to multiply the numbers. This is easy. I don't need a calculator for this. It's 4.8 times. Now we have to multiply the powers of 10. They have the same base. So I copy the base. And what happens to the exponents?
Add it together.
Add them. So 7 minus 3 is 4. This is already in scientific notation. This is it. I don't have to do anything else. If the result were not in scientific notation, then I had to make some adjustments. If we don't get an example like that, I will show you one. Any questions on this problem?
So you do not multiply the 10 and the 10. You keep the base the same. And only
This is the exponential rule.
Right. Okay.
This is like x to the third times x to the fourth is x to the seventh.
Right. Okay. Thank you.
Because they are the same, they have the same base. Otherwise, I can't. But they have the same base. Okay.
So the second part where it says 2 to the 10 negative 3, is it supposed to be 2.0?
Yes. So 2 times 10 to negative 3 or 2.0 times 10 to negative 3 is the same. Yeah. Good. Let's continue. 21. Aha. Let's work on this. So 12.9 times 10 to negative 8. Everything divided by 3 times 10 to negative 4. Perfect. Good. This part is easy because I copy the base, and what happens to the exponents?
Subtract 8.
Negative 8 minus minus 4 will be negative 4. Negative 8 plus 4 is negative 4. Okay, now 12.9 is divisible by 3, so I get 4.3. 12 divided by 3 is 4, and 9 divided by 3 is 3. This is already in scientific notation. No adjustments are needed.
It's when it does become scientific notation.
Yes. In certain situations, we have to do the work. Yeah. Okay, determine whether or not the given number is written. No, the given number is not written in scientific notation. We will. Okay. So, this is not written in scientific notation because the scientific notation cannot accept 0 as the first digit. So, obviously, I have to move the decimal point one spot to the right. And I either write 8 or I write 8.0. It doesn't matter. They mean the same thing. But now, careful, because I increased the number, multiplying it basically by 10. So I have to reduce this by 1 digit. The number was 0.8. I increased it by a power of 10. From 0.8, I multiplied by 10 to get 8, which means I borrowed from here. I took a 10 from 10 to the 6th. This is the same thing with 0.8 times 10 to the 6th power. Dana thinks that the number is correctly written in scientific notation. Is she correct? No. So we have 683.5 times 10 to the 5th. And we want to put it in scientific notation, which means I have to move the decimal digit 2 to the right. I meant left, the other right. So 6.83. So I had a big number. I had 600, but now I change it into 6. What did I do? I diminished it by a power of 100. I divided by a power of 100. So I have to increase this power by 2. I diminished the number by 100. If I diminished it by 100, I have to increase the power. Let's see what the calculator does. I'm just curious now. I've never done this before with the calculator. I never needed to, but now it's a question. Let's see what happens if we write 683.5 EE 5. I'm just curious to see if it changes it correctly. It should. Oh, it doesn't. It changes it into the standard notation. But that's okay. Because see, 2, 4, 6, 7. So this is 6.835. Oh, I forgot to write the 5. Oh, there was no 5. Oh, yeah, I forgot to write it here. Times 10 to the 7th power. So you can also check like that. Okay?
I did have a question.
Yes, please.
It pertains to calculus. Do you use any leading zeros or trailing zeros in your calculations?
Leading zeros and trailing zeros in calculations. You mean you're talking about calculus? You're talking about limits, maybe?
Yeah, like like the 0.0034. Like, do you ever use that in calculus when you get the calculus?
Well, it depends on the problem. The answer is yes.
Okay.
It depends on the problem. It depends on whether we are asked to approximate the answer.
So
Fine.
more like a physics type of problem.
So it depends. So for example, if they want an exact answer, let's say 1 over 2 pi is the exact answer, let's say in cubic centimeters per second, for example, then I may be asked to approximate it. And I may or may not have to write it in scientific notation. So if I have to divide 1 by, in parentheses, 2 times pi, as an example, it's a very good question, then this is the answer. And normally they don't ask it in scientific notation. They ask to approximate to 3 decimal digits. But the reason we talk about the scientific notation is mainly to understand, I think, how to use the calculator and how to read the calculator. Because the calculator has limitations.
Okay, thank you.
But if I come across something that I can think of about this, I'll let you know. Okay, so now the tenths are very easy because we copy the base and we add the exponents. So now we have to multiply 4 by 1.5. And what do we get?
6.
So since there is nothing else, it's just simply 6 times 10 to the 8th power. There is nothing else. This is already scientific notation. You can write it as 6.0 if you want, but 6 times 10 to the 8th is good enough. Okay?
Will it ever happen where the bases are not the same? Like it's not a 10 and
But
a
that's
10?
not an exponential notation. The exponential notation has to have 10.
Perfect.
It has to have a power of 10. It cannot have a power of 8
Okay, that makes
or
sense.
2 or 3. So these will always be the same base
Perfect.
if they are in scientific notation. Okay? Okay, this is an interesting one. So 1.2 times 10 to 0 multiplied by 6 times 10 to negative 3. This is a little bit of a silly type of example, but that's okay. Well, I know what 10 to 0 is. 1. So I only need to multiply 6 by 1.2, which is 7.2 times 10 to negative 3, because there is nothing else. And this is indeed in scientific notation already. Okay, a few more, 5 more. Okay, this is a good one again. It's a division. And this is 42 times 10 to the 15 over 6 times 10 to the 9th. And again, this is an easy situation though, because this division is 7 times 10 and 15 minus 9 is 6. And this is already in scientific notation. Good. Okay, this is the same thing, so it's 3 times 10 to the 12th. There is no problem there. Okay, yes, let's work on this one. So 2 times 10 to negative 3 over 8 times 10 to negative 7. Okay. When I simplify by 2, I know that 1/4 is 0.25. This is a quarter. Now the 10th are easy as well. So this is 10, negative 3 minus negative 7 is 4. But this is not in scientific notation. So here we're going to borrow a 10 from this bunch, because we need to move the decimal digit 1 spot to the right. So this will be 2.5 times 10 to the 3rd power. I'm curious now what the calculator gives on this one. Bear with me 1 second. So, in parentheses, 2 EE negative 3 divided by, in parentheses, 8 EE negative 7. I'm curious to see how the calculator will handle this. Okay, so it's 2.5 times 10 to the 3rd.
Interesting.
2.5 times 10 to the 3rd. Good. Last few examples here. I know we had enough of this. Ah, let's also look at this. So 7 times 10 to the 8th, everything squared. This is a good one. Let me look at 30. Okay, well, let me copy 30 as well. 6 times 10 to the 7th, and 4 times 10 to the 4th. And the last one. Okay, why not? 10 to the 8th, 4 and 10 to the 6th, and this is squared, over 4 times 10 to the 4th. Okay, let's take it slowly. Let's go back to the first one. So here I see 2 factors. I have to raise both factors to the 2nd power. So I have 7 times 10 to the 8th. Everything squared. I have to raise 7, and I get 49. I copy the base, and I have to multiply the exponents. So I get 16. This is all good, but it's not in scientific notation. So this is, so to speak, a large number. I have to make it into a small number, meaning I'm dividing by 10. So then I have to increase the power by 1. So this will be 4.9 times 10 to the 17th. Okay, the second one. Any questions on the first one? Okay, so now I have to multiply 4 by 6 by 4. What do we get when we multiply 24 by 4? 96?
Yes.
96. So now 10 to the 6th, 10 to the 7th, 10 to the fourth. So this means times 10 to, these two are 10 plus 7, 17. So this again is not scientific notation. This number is not presented in scientific notation, which means I have to move the decimal point to the left one, meaning I'm dividing. If I'm dividing by 10, I have to also multiply by 10. So I have 9.6 times 10 to the 18th. On the last one, and since I don't have enough room in here, I'm going to copy it on the next page. So 1 times 10 to the 8th, 4 times 10 to the 6th squared, over 4 times 10 to the 4th. So first of all, 1 times 10 to the 8th stays as is. I have to square 4, and I get 16. I have to square 10 to the 6th, and I get 10 to the 12th power. The denominator is 4 times 10 to the 4th. I know you remember I said, please never multiply before you try to simplify. And of course, they're all factors. I'll simplify by 4. I have 4 times 1 in the front, so it's 4. And now I have power 8 plus 12 is 20. Subtract 4. So times 10 to the 16th power. Let's see what the calculator does with this. I'm curious again. Last one. This is the last one, and then we move on. Careful with parentheses, please. You don't have to write 1 times 10 to the 8th. Just put EE 8. The next one is 16 EE to the 12th. And then divided by, in parentheses, 4. And EE to the 4th power. The calculator has on this number has to use the exponential, the scientific notation, because this is such a huge number that the calculator should not be able to present otherwise. So when I click enter, I am hoping that the calculator will present 4E16. It has to, because this is such a huge number that the calculator cannot handle it in any other way. Any questions? Okay, perfect. Okay, so this is done. I think we have it. And we finally get to, notice that there is no practice for dividing polynomials by binomials. There is no practice, there is just learn. So we're going to go to it. But they only want us to divide polynomials by binomials. And I want to show you 2 methods. And that's the end of Mod 5. And we will start Mod 6 with the handouts that I sent you. I don't like any of the sequence of presentations. Ever. I never, in any of the books that I taught from in many, many, many years, I never liked the way this is structured. So that's why I have my own handouts. We'll finish factoring and then we'll go back and practice with everything that they have here. Okay, so let's talk about the last section, which is 5.7 of Mod 5, dividing polynomials by binomials. And we have 2 methods. One that works always and forever, and the other one that has limited applicability. One of them is called long division. And this works forever and ever. The other one has limited applicability, and it's called, it's the synthetic division. So when we have a polynomial p of x, so that's why I'm saying it has limited applicability. So only when we divide a polynomial by x minus a number. Okay? It works only in this situation. If we have x squared plus, it doesn't work. It has to be a term, it has to be a binomial that has degree 1. It's called synthetic division. Okay, we'll start with the long division, and then we'll find examples for specific that work specifically with this. This works forever, all situations. This one does not, only in these cases. Okay, so let's talk about the long division. I want to show you a numerical example. I know we no longer do this by hand. I just want to show you a numerical example so you understand the mechanism. Let's say 5321 divided by 25. The long division is identical with this. It's the same mechanism. It's the same algorithm. But of course it will look differently because of x and whatever else, you know, other variables, right? So, but it's the same mechanism. So, 25 goes into 53 twice. I go back and distribute, multiply. 2 times 25. I write underneath the like term, so to speak, but 2 times 25 is not negative 25, but I have to change the sign because I subtract. Again, 2 times 25 is not negative 50, but I have to change the sign every time I write underneath. I bring down the next in line. I bring down the next in line. I perform the operations I see, and then I bring down the next in line. 25 goes into 32 once. I go back and I distribute. 1 times 25 is not negative 25, but I have to change the sign because I have to subtract. I perform the operations I see, and I get a 7 and nothing else, and I bring down the last in line. 25 does not go, 25 into the 71 is not 3 because there will be 75, so I have to stop at 2. Again, 2 times 25 is not negative 50, but I have to change the sign because I need to subtract. So the answer is 21. I box in 21 because this is the remainder of the division. So what did I just do? I divided 5321 by 25. I got the quotient 212 plus, why plus? Because 21 is positive, right? Plus 21 over 25. This is called the quotient. This is called the remainder. And this is called the divisor. With numbers, however, we are going to write the answer as 212 and 21 over 25. But for polynomials, this symbol cannot be omitted. This is a must be there, either positive or negative for polynomials, not for numbers. Because we don't write it like this, we write it like a mixed number. Okay, the same mechanism we are going to apply. I always present this because students ask me, but why did you change the sign? I understand. 2 times 25 is not negative 50, but I have to change the sign because I have to subtract. The same procedure applies here. Ready? 2x to the third plus x minus 3x squared plus 2 divided by x minus 1. Notice one thing. If I had only one term, I would have split the fraction and simplify each fraction by itself. But this time it does not work. So I look at this division and I have to ask myself two questions before I start the algorithm. And here are the questions. Question number 1, both in descending order? If not, rearrange. If not, rearrange. They're not. The denominator is, but the numerator is not. So 2x cubed minus 3x squared plus x plus 2 divided by x minus 1. This is the first step, mandatory step. I cannot start without this. Second question before I start the algorithm is missing term or terms in the numerator? We talked about this some time ago when we arranged everything in descending order in a polynomial. And every now and then I said, is there a missing term? Who cares if there is a missing term? Now we do. We're going to look at an example with missing terms and you'll see what happens. In this particular case, no missing term. I know the degree is 3. Degree 3 is there. Degree 2 is there. Degree 1 is there. Degree 0 is there. No missing term. So this is a situation in which I don't have to worry about it. Not in this case. Okay. So therefore, I can start the algorithm. Here's the algorithm. 2x to the third minus 3x squared plus x plus 2 and x minus 1. It's the same procedure. It will look differently though because of variable and because of two terms. Because we have two terms in the divisor. All this is possible because we know exponential rules. That's why we study. That's another reason why we study the exponential rule, so we can get this done. So here it is. X times what is 2x cubed? At the top, we never lie. At the top where the quotient lies, we never lie, so to speak. I'm asking myself, 25 times what is 53, and it has to be 2. But when I write it underneath, I have to change the sign, no matter what, to the opposite sign. Okay, so 2x squared. One other remark here before we continue. If the first term has degree 2, the next one must have degree 1. The next one must have degree 0. You cannot go backwards. So if this is degree 2, the next one cannot be degree 4 or 5 or 6. So the degree of the answer of the quotient is 2. Everything else that follows has to be a weaker and weaker and weaker. Okay, which is not the case here. Okay, perfect. So now we go back. We distribute to both terms. Change the sign because we subtract to the opposite sign. Okay? 2x squared times x is 2x cubed, but I have to subtract. 2x squared times negative 1 is negative 2x squared, but I have to subtract. Meaning, every time I write below the like term, I have to change the sign from whatever to the opposite. Perform the operations I see. Nothing. negative x squared. I bring down the next in line. I do not lie right now. X times what is negative x squared? Negative x. I go back and distribute. Negative x times x is negative x squared. I don't care. I have to change the sign to the opposite. Negative x times negative 1 is positive x. I don't care. I have to change the sign to the opposite. Bring down the next in line. I have to stop. Because x minus 1 does not go into 2. 2 has to be boxed in. 2 is the remainder. So, coming back to this division, the quotient 2x squared minus x plus the remainder over the divisor. Is it true? I don't know. Can I check? Of course. Absolutely. So here's how I check. If I have 10 divided by 3, I know that this is 3 integers plus 1/3. How do I check this? 3 times 3 is 9 plus 1 is 10. The same thing here. I will multiply x minus 1 by 2x squared minus x and add 2. If that multiplication and adding 2 gives me back the numerator, this is okay. If it does not give me back the numerator, I'll say, oops, start from scratch. So, 2x squared minus x multiplied by x minus 1 and plus 2. If this does not give us 2x cubed minus 3x squared plus x plus 2, then the whole thing makes no sense. It's incorrect. So I'm checking. Understand that this would have not been possible if we hadn't studied multiplication of polynomials.